There's a moment, usually late at night, when you look up at the stars and something old and uncomfortable stirs inside you. Not wonder exactly, not awe. Something more primal than either of those. The feeling that you're being watched. It doesn't make rational sense. You're standing on a small planet orbiting an ordinary star in the outer edge of one galaxy among 2 trillion. The idea that something out there is looking back at you specifically seems absurd, except scientists are no longer so sure it is. Because when you take what we know about the age of the universe, the number of stars, the chemistry of life, and the mathematics of probability, and when you take what we know about how civilizations develop and what they're capable of at extreme levels of advancement, the question of whether something is watching us stops being philosophy and starts being physics. And the answer that keeps emerging from the data is strange. Not probably not maybe, but something more unsettling. We genuinely cannot rule it out, and some of the evidence suggests we should be taking it much more seriously than we do. In this video, we're going to look at the actual science behind cosmic observation. We're going to examine the Fermi paradox, the mathematics of civilizations, the anomalies our telescopes have found, and the theories, some disturbing, some beautiful, that attempt to explain whether something out there has been watching us for a very long time. By the end, you'll see why this isn't a fringe question. It's one of the most serious questions in modern astrophysics. And the silence from the cosmos may not mean what we think it means. Let's get into it. Section 1. The scale of possibility. To understand whether something might be watching us, you first have to truly grapple with what we're embedded inside. Not just understand it intellectually, but feel it. Because human intuition is built for savannas and social groups, not for the kind of numbers we're dealing with here. The observable universe, the portion we can actually detect, is about 93 billion light-years across. That number sounds big, but it doesn't land the way it should. So let me try a different approach. If you took every grain of sand on every beach and desert on Earth, you'd have roughly 10 quintillion grains. 10 with 18 zeros. That sounds like a lot. And it is. It's fewer than the estimated number of stars in the observable universe. Current estimates put the stellar census at around 200 sextillion stars. That's a 2 followed by 23 zeros. Every grain of sand times 10,000. And we now know, not suspect, not theorize, but know, that most stars have planets. The Kepler Space Telescope spent years staring at a small patch of sky and found that planetary systems are the rule, not the exception. When you apply that finding to 200 sextillion stars, you get a number of planets so large it becomes essentially meaningless to the human mind. Now here's the part that matters for our question. The universe is 13.8 billion years old. Our sun is 4.6 billion years old. That means there are stars that formed, lived, and died before our sun even ignited. Stars that had planets around them billions of years before Earth existed. If life is at all possible, and we have strong evidence it is, given that it emerged on Earth almost as soon as conditions allowed, roughly 3.8 billion years ago. Then there has been an extraordinary amount of time for it to develop, proliferate, and advance on other worlds. The question isn't just, does life exist elsewhere? It's something deeper and more alarming. what has life had time to become elsewhere? Consider what our civilization has accomplished in roughly 10,000 years of organized society and about 300 years of science. We split the atom. We sent machines to other planets. We decoded our own genome. We built global communication networks. We are actively developing artificial, general intelligence. Now imagine a civilization that had an additional million years. Not 1,000 years, 1,000,000. The gap between us and that civilization would be larger than the gap between us and the bacteria in our gut. Such a civilization could, in principle, have mapped every star in the galaxy, monitored every planetary system, detected the atmospheric signatures of life on every habitable world. They could have been aware of Earth for millions of years before the first dinosaur walked on it. They could be watching right now, and we would have no idea. This is the backdrop against which every serious discussion of cosmic observation has to be set. Not, are there other civilizations? But given the scale and age of the universe, what might the most advanced civilizations be capable of, and what does that mean for us? Section 2. The Fermi Paradox. The question that won't go away. In the summer of 1950, 4 physicists were eating lunch at Los Alamos National Laboratory. They were joking about a recent newspaper cartoon. Aliens stealing garbage cans, if you can imagine it. The conversation drifted, as conversations among brilliant physicists sometimes do, towards the question of extraterrestrial intelligence. One of the 4 men, Enrico Fermi, had already won the Nobel Prize. He was known for his ability to make startlingly accurate estimates from very little information, a skill called Fermi estimation. And somewhere between the soup and the main course, he turned quiet. Then he asked a question. Where is everybody? It was a simple question, but the simplicity was deceptive because embedded inside it was a problem that has never been solved. Fermi had reasoned through it quickly, the way he reasoned through everything. The Milky Way is enormous, roughly 100,000 light-years across, but it's also ancient, about 13 billion years old. If even one civilization had emerged anywhere in the galaxy and developed interstellar travel, even slow interstellar travel at a fraction of the speed of light, it would have had time to colonize every star system in the galaxy multiple times over. The math isn't speculative. At 1%, the speed of light, far slower than what relativistic physics allows, a ship would reach the nearest star in 400 years. Colony ships could then send further colony ships. This exponential expansion means a single civilization starting anywhere in the Milky Way could theoretically fill the entire galaxy within a few million years, maybe 10 million on the slow end. But the Milky Way is 13 billion years old. That's 1,300 cycles of 10 million years. If any civilization ever developed interstellar travel and the inclination to expand, the entire galaxy should be colonized by now, including our solar system. And yet, silence, no megastructures, no signals, no obvious signs of alien modification of any stellar system. The cosmos appears pristine, unmodified, natural. This is the Fermi Paradox. And it's not a paradox in the sense of being a logical impossibility. It's a paradox in the sense of an expectation dramatically violated by observation. We expect the galaxy to be teeming with evidence of civilization. Instead, we find none. the answers proposed by serious scientists over the decades fall into a few broad categories. The first, we are alone. Life is an extraordinarily rare accident. The emergence of intelligence is rarer still. Perhaps in this entire observable universe, the right conditions aligned in the right sequence on exactly one world, ours. The silence isn't a mystery, it's the answer. The second, they all died. Life emerges frequently enough. Intelligence emerges. Technology develops. And then something kills them. Every time. Before they can spread, before they can leave a permanent mark, some catastrophe, internal or external, terminates each civilization. This is called the Great Filter. And the terrifying implication is that if the filter is in front of us rather than behind us, we're probably next. The third, they exist, but they're not doing what we expect. Advanced civilizations don't broadcast radio signals because radio signals are primitive technology they left behind millions of years ago. They don't colonize the galaxy because they have no need to. They've transcended physical expansion entirely. They're there, but invisible to our instruments and incomprehensible to our frameworks. The fourth, and the one most relevant to our question, they're watching. They're present. They know we exist. And they've chosen, for reasons of their own, not to make themselves known to us. Each answer is disturbing in its own way, but the fourth is the one that carries the most implications for how we should be thinking about our place in the cosmos. Section 3, the Zoo Hypothesis, Earth as a Nature Preserve. In 1973, an MIT radio astronomer named John Ball published a paper that proposed a specific and unsettling solution to the Fermi paradox. He called it the Zoo Hypothesis. The idea is this: there are advanced civilizations out there. They know we exist. They've been watching us for a long time, and they've deliberately chosen not to intervene, not to contact us, not to reveal themselves, because they want to observe natural development. We are, in this framing, something like a nature preserve, a protected wilderness, and the beings who established that protection are the keepers. This isn't as outlandish as it might sound. We do exactly this with other species on Earth. We set aside nature reserves. We observe animal behavior from blinds so we don't disturb the subjects. We have strict protocols in wildlife research about not interfering with natural behavior. We debate the ethics of intervening even when we observe suffering, because we understand that intervention can have unintended consequences. A civilization millions of years older than us would look at us roughly the way we look at a community of chimpanzees, intelligent, fascinating, worth studying, but not ready for contact on equal terms. Ball's hypothesis carries a specific prediction. If it's true, there would need to be something like a galactic policy, an agreement among advanced civilizations that young, developing worlds are off limits for contact. Like a treaty in a nature preserve, you can watch, you cannot interfere. This agreement would explain the Great Silence. It's not that everyone is absent. It's that everyone has agreed to be quiet around us specifically. There's a creepy refinement of this idea developed by later researchers, the planetarium hypothesis. This version proposes something more active than passive observation. What if advanced civilizations haven't just agreed to stay quiet, but have actively constructed our observable universe to appear empty? What if the cosmic microwave background, the apparent emptiness of the galaxy, the silence on all radio frequencies, What if all of this is an engineered illusion designed to keep young civilizations from knowing the truth about what's out there? This sounds like paranoid science fiction, and it might be, but here's the uncomfortable philosophical point. If it were true, we would have no way of knowing. Every piece of evidence we gathered would be consistent with the illusion, because the illusion is designed to be consistent with itself. We can't rule it out. Not because the evidence supports it, but because the hypothesis is specifically constructed to be immune to disproof from within the system it describes. What we can do is ask, what would we expect to see if the zoo hypothesis were true? And does what we observe match those expectations? The zoo hypothesis predicts no signals addressed to us, no megastructures in our own system, possibly subtle signs of monitoring activity just beyond our detection threshold, and possibly an increasing trickle of anomalies as our technology improves. Things that don't quite fit natural explanations, but that fall just short of constituting proof. Look at the last 50 years of astronomical observation. What have we found? No clear signals addressed to us, no megastructures in our solar system, an increasing trickle of anomalies, things that don't fit natural explanations, but fall just short of proof. It's not confirmation, but it's uncomfortably consistent. Section 4. The dark forest watching as a prelude to something worse. The zoo hypothesis is unsettling, but relatively benign. The universe's most advanced civilizations are watching over us like protective wardens. We're in a preserve. It's not flattering, but it's not threatening. But there's another solution to the Fermi paradox that takes a much darker view of what cosmic observation might mean. And it has gained serious scientific traction since it was popularized by Chinese author Liu Cixin in his novel, The Three-Body Problem. It's called the dark forest theory. The logic begins with resources. The universe contains finite matter, finite energy, finite space. Every civilization needs these things to survive and grow, and every civilization that advances far enough will eventually face a resource ceiling, a point beyond which it must expand or begin to die. Now add uncertainty. When you're a civilization that has been around for millions of years, you've developed a particular kind of wisdom. You cannot trust what you cannot verify. You can receive a signal from another civilization. You can analyze that signal for 1,000 years. But you cannot ever be completely certain of their intentions. You cannot verify that a species advertising cooperation isn't planning competition. And finally, add stakes. If you extend trust to a hostile civilization, you may be exterminated. The downside is total and irreversible. If you eliminate a peaceful civilization out of excessive caution, you've committed a terrible act, but your civilization survives and can correct course. The asymmetry of these outcomes drives rational decision-making in a chilling direction. Under these conditions, Liu Cixin argues, every sufficiently advanced civilization converges on the same strategy: silence, concealment, and preemptive elimination of any civilization it detects that might eventually pose a threat. The universe is a dark forest. Every civilization is a hunter, moving silently through the trees, weapons ready. The sound of footsteps means danger. Any light in the darkness is either a trap or a target. Civilizations that broadcast their location survive only until they're found, and they are always, eventually, found. Under this framework, the Great Silence is not peaceful. It's the silence of an arms race played on geological timescales. Every civilization that has lasted has learned to be invisible. Every civilization that failed to learn that lesson is gone. And if this is true, the implications for us are severe. We have been broadcasting radio signals since the 1930s. Our radiosphere, the expanding bubble of electromagnetic radiation advertising our existence, our location, our technology level, and our complete unawareness of the danger, is now about 200 light-years in diameter. Anyone within 100 light-years of us knows we're here. They've known for decades. They've been watching. Under the zoo hypothesis, this is fine. We're protected specimens. Under the dark forest theory, we have painted ourselves as targets. Stephen Hawking was genuinely alarmed by this possibility. He made the comparison to European colonization of the Americas. Technologically superior civilizations encountering less developed ones, with outcomes that were, from the perspective of the less developed, catastrophic. Meeting an advanced civilization could be bad for us, Hawking said, in the same way that it was bad for Native Americans when Columbus arrived. Several physicists and astronomers have publicly opposed active SETI, the deliberate transmission of powerful signals toward other stars, specifically because of this concern. Not because they're certain the dark forest is real, but because the asymmetry of risk is severe enough that caution seems warranted. If the dark forest is wrong, we lose nothing by being quiet. If it's right, broadcasting our location could be the last thing our civilization does. Whether you find the dark forest compelling or paranoid, it forces a crucial question. If someone is watching us, what are they doing with the information? Protecting us? Judging us? Preparing for us? And how would we know? Section 5. The wow signal. The moment we may have heard something on August 15th, 1977, a volunteer at the Big Ear Radio Observatory in Ohio was reviewing a printout of radio telescope data. His name was Jerry Eman. He'd been doing this for months. Most of it was noise, background static from the cosmos, occasional interference from Earth-based sources, the usual electromagnetic hiss of the universe going about its business. Then he saw something that made him stop. In the margins of the printout, he circled the sequence of characters and wrote one word. Wow. The sequence was 6EQUJ5. To understand what that means, you need to know that the printout used a system where numbers represented signal strength, 1 through 9 for weak signals, and letters starting from A for anything above 9. The letter U represents a signal about 30 times stronger than the background noise. Whatever Big Ear had detected had risen dramatically from baseline, peaked at a level of extraordinary intensity, and then declined. The shape of the signal, the way it rose and fell, matched exactly the pattern you'd expect if a radio telescope swept past a fixed point source in space. Not something in our atmosphere, not something orbiting Earth. A fixed source, far away, broadcasting in a very specific direction. The signal was detected at 1,420.4556 megahertz, almost exactly the frequency at which hydrogen emits radio waves. This frequency is not coincidental. Hydrogen is the most abundant element in the universe. Any civilization capable of radio astronomy would know about hydrogen emission. Any civilization trying to make their signal maximally detectable to other civilizations would choose a frequency near this cosmic landmark. SETI pioneers had predicted decades earlier that this was the most likely frequency for an interstellar signal. The logic was, if you want someone to answer the phone, you put the phone where people are likely to look. The signal lasted exactly 72 seconds, the maximum time Big Ear's fixed position on Earth's rotating surface allowed it to observe any single point before it rotated away. And then it was gone. Astronomers have pointed instruments at that exact patch of sky hundreds of times since 1977, using the most sensitive radio telescopes on Earth. Over many decades, no signal has ever been detected again. The WOW signal remains the strongest candidate in the history of SETI for a signal of extraterrestrial intelligence. It matched every prediction that researchers had made for what such a signal would look like. Its source remains unidentified. No natural explanation has been widely accepted. In 2016, researchers announced they had found the source, comets. 2 comets passing through the field of view could have produced a hydrogen emission signal. The astronomical community received this explanation with what you might diplomatically call skepticism. The proposed comets were not in the field of view at the right time. The geometry didn't quite work. The frequency matching was not as clean as claimed. The cometary explanation has largely been set aside. The WOW signal remains unexplained. What we know for certain, something produced a powerful, brief, narrowband radio signal from a direction in space. It appeared once, it has not appeared again. It had properties consistent with intelligent origin. It had no identified natural source. What we cannot say with certainty, anything beyond that. But here's the thought that stays with me about the WOW signal. We've been systematically searching for extraterrestrial signals for about 60 years. We search a tiny fraction of the sky at any given time, at a limited range of frequencies, with imperfect equipment. The probability of catching a brief signal from a distant source in any given moment is extremely small. And yet we may have caught one, once, in the first few decades of looking. If signals like the WOW signal are being broadcast continuously by many sources, we should be detecting them regularly with better equipment. If they're rare and brief, we may have stumbled onto one by extraordinary luck. Either way, the WOW signal tells us something important. The cosmos is not obviously, definitively silent. It gave us one data point, one moment, that didn't fit. And that one moment is enough to ensure that the question of whether something is out there cannot be answered with a confident no. Section 6. Technosignatures. What watchers would leave behind. For most of SETI's history, the search focused on deliberate signals, an alien civilization actively trying to communicate. Tune to the right frequency, listen in the right direction, and catch the call. But in recent years, a much broader approach has emerged. One that doesn't require any civilization to be trying to reach us. One that might reveal civilizations simply by the side effects of their existence. The concept is called technosignatures, detectable signs of technology regardless of intent. Think about what we leave behind. Earth, observed from 1,000 light years away with a sufficiently advanced telescope, would look unusual in several ways. Our atmosphere contains oxygen in unusual abundance, created by biology and maintained by photosynthesis. It also contains industrial gases, chlorofluorocarbons, nitrogen dioxide in concentrations impossible without combustion, a suite of synthetic chemicals that have no natural pathway to formation. Our radio bubble extends outward at the speed of light. Our cities light the night side of the planet with a spectral signature unlike anything natural. We are accidentally broadcasting our existence in a dozen ways simultaneously. We're not trying to be detected. We can't help it. Now imagine what a more advanced civilization would leave behind. Freeman Dyson, one of the most creative physicists of the 20th century, proposed in 1960 that a civilization advanced enough to exhaust the energy of its home planet would eventually build a structure to capture the full output of its star. A shell, or more realistically, a swarm of solar collectors, encasing the star entirely. A Dyson sphere, as it came to be called, would transform a star's energy output from visible light to infrared radiation, waste heat radiated by the shell. From a distance, you'd see a star that had gone dark in visible wavelengths but was blazing in infrared. An impossible signature? Nothing natural looks like that. In 2015, astronomers discovered a star that seemed to do something even stranger. KIC 846282, quickly nicknamed Tabby's star after its discoverer, Tabitha Boyajian, showed irregular dips in brightness completely unlike any known natural phenomenon. Most planet transits dim a star by less than 1%, briefly and predictably. Tabby's star dimmed by up to 22% at irregular intervals for irregular durations. When the news broke, the immediate reaction, before the cautious scientific hedge, was, "This looks like a megastructure under construction." The paper describing the discovery was careful. It listed natural explanations first: comets, dust, unusual debris fields. But the lead author herself admitted that nothing natural quite fit the data. The scientific community spent years trying to resolve Tabby's star. Thousands of amateurs and dozens of professional astronomers pointed instruments at it. Eventually, the consensus settled on circumstellar dust in unusual configurations as the most likely natural explanation. But most likely is not the same as definitively. And the episode revealed something important. Our telescopes are now good enough to detect things that don't fit our models. Things that require us to ask the question out loud, in peer-reviewed journals, whether we might be looking at technology. That threshold has been crossed. The era when, could this be artificial, was not a scientifically serious question is over. SETI has expanded in the last decade to include systematic technosignature searches. Teams are looking for anomalous stellar dimming patterns inconsistent with natural processes, excess infrared radiation from stellar systems, the waste heat signature of a Dyson structure, unusual chemical signatures in exoplanet atmospheres, not just biological markers, but industrial ones, laser, pulses in optical wavelengths that don't match known stellar phenomena, radio signals with structure, with encoding, with patterns inconsistent with natural sources. The James Webb Space Telescope, now operational, can analyze the atmospheres of exoplanets with a precision previously impossible. It can detect biological signatures. And it can detect technosignatures, industrial chemicals, for instance, that no natural process would produce. We haven't found confirmed technosignatures yet, but the tools are now powerful enough that we would recognize them. and we're looking systematically in a way we never have before. If something is out there, watching or simply existing, we are closer than we have ever been to seeing its shadow. Section 7. The Mathematics of Ancient Civilizations. Let me introduce you to a calculation that I think is one of the most underappreciated ideas in modern astrophysics. It's called the astrobiological Copernican principle, and it was laid out in a 2020 paper by astronomers Tom Westby and Christopher Conselis at the University of Nottingham. The argument starts from a simple assumption. We have no reason to think Earth is special. The conditions that gave rise to intelligent life on our planet, the type of star, the position in the galaxy, the age of the system, the chemistry of the planet, should exist elsewhere. And wherever they exist, they should produce intelligent life on similar timescales. That's the Copernican part. We're not exceptional, we're typical. From this assumption, Westby and Conselis tried to estimate the number of communicating civilizations in the Milky Way. Their answer, under conservative assumptions, was about 36. There should be about 36 technological civilizations capable of communication in our galaxy right now. 36 is a small number. It means they're very spread out. The average distance between them would be roughly 17,000 light-years. At that distance, a round-trip radio conversation would take 34,000 years. But here's what the calculation implies that the authors didn't emphasize, and that I want to sit with for a moment. If there are 36 civilizations in the Milky Way today, how many have there been over the galaxy's history? Stars have been forming for 13 billion years. Habitable planets have existed for billions of years. If civilizations arise and fall on timescales of thousands to millions of years, the total number of civilizations that have ever existed in the Milky Way could be enormous. Hundreds, thousands, tens of thousands. Most of them would be gone, extinct before we were born, long before the dinosaurs, long before the first complex multicellular life on Earth. But some of them might have lasted, or left things behind that lasted. In biology, we have a concept called convergent evolution. When different lineages independently evolve the same solution to the same problem. Eyes evolved independently in vertebrates and cephalopods and insects because eyes are a good solution to the problem of detecting light. Wings evolved independently in birds, bats, and insects because wings are a good solution to the problem of flight. In the context of civilizations, if you have tens of thousands of intelligent species across billions of years of galactic history, some of them will find solutions that are very, very durable. Some will develop technologies or strategies for long-term survival that work. Not because they're special, but because given enough trials, solutions that work will appear. Some of those civilizations, the ones that found durable solutions, might still exist, might have been around for millions of years, might have accumulated capabilities so far beyond ours that the comparison strains the concept of civilization. And here's what makes this calculation eerie when you think about our specific question. If a civilization has been around for even 1 million years, and if it has technology that scales with time the way ours does, it would have capabilities we literally cannot conceive of. We've had astronomy for about 400 years, radio technology for about 130 years. We've gone from horse-drawn carriages to interplanetary spacecraft in less than 200 years. What does a civilization with a million-year head start look like? What sky would they see when they look at us? And what are they thinking? Section 8. Oumuamua, the object that shouldn't exist. On October 19th, 2017, astronomers at the Pan-STARRS telescope in Hawaii detected a faint point of light moving across the sky at an unusual speed. Within days, they realized this was something the solar system had never seen before, an object that had come from outside, from interstellar space. They named it Oumuamua, a Hawaiian word meaning scout or messenger, arriving first from afar. It was moving fast, too fast, in fact, to be gravitationally bound to the sun. It was already on its way out of the solar system when we found it. We caught it at its closest approach to Earth, then watched it recede. What we observed in those weeks of observation was deeply strange. The object's brightness varied dramatically, by a factor of 10, as it tumbled through space. This variation implied a shape wildly unlike any asteroid or comet we'd ever seen. The best models suggested an aspect ratio of at least 5:1. It was either extremely elongated, like a cigar, or extremely flat, like a pancake. Neither shape is consistent with how natural objects form. Natural rock objects, asteroids, comets, fragments of planetary collisions, form through collisions, gravitational accretion, and gradual erosion. These processes produce irregular but roughly equidimensional shapes. Not flat disks, not slender cigars. The physics of how rocks form simply doesn't produce things that look like Oumuamua. But the shape was not the strangest thing. As astronomers continued tracking Oumuamua, they noticed that it was not following the trajectory that gravity alone predicted. It was accelerating, moving faster than it should, and it was doing so without producing any detectable outgassing. Comets accelerate when they approach the sun because the sun heats their surface, releasing gases that act as rocket exhaust. This outgassing is visible. You see the comet brightening, developing a tail, releasing dust and vapor that can be detected spectrally. Oumuamua showed none of this. No coma, no tail, no detectable volatiles of any kind. Just clean, unexplained acceleration that precisely followed the inverse square relationship, with distance from the sun you'd expect from a pressure driven by light. Exactly what you'd expect from a solar sail. Avi Loeb, the chair of Harvard's astronomy department and one of the most credentialed astrophysicists in the world, analyzed the data and reached a conclusion he published and has defended ever since. Oumuamua's properties are most consistently explained as a piece of alien technology, specifically a light sail, a thin, flat sheet of reflective material pushed by photon pressure from the sun. The scientific community's reaction was fascinating. Most researchers were deeply uncomfortable with the conclusion, not because the data was wrong. Loeb's data analysis was sound, but because alien technology felt like a conclusion too far. Extraordinary claims require extraordinary evidence, and while Oumuamua was extraordinary, it hadn't crossed whatever threshold would make the extraordinary explanation acceptable. Various natural explanations were proposed. Hydrogen ice, a form of ice that's nearly undetectable but would produce acceleration through outgassing. Dust bunnies, loosely bound aggregates that would have low density and unusual behavior. Solar radiation pressure. but the numbers only worked for objects implausibly thin by natural standards. None of these alternatives has been widely accepted. None is fully consistent with all the observations. Loeb's position has been consistent. We have an object that came from interstellar space, with a shape unlike anything natural we've ever seen, exhibiting acceleration consistent with a light sail and inconsistent with all proposed natural alternatives. The scientific principle of following the evidence wherever it leads should, at minimum, leave the possibility of artificial origin on the table. He wrote a book about it. Extraterrestrial, the first sign of intelligent life beyond Earth. In it, he argues that the scientific community's resistance to considering artificial explanations reflects not scientific rigor, but social discomfort, a kind of academic risk aversion where being associated with the alien hypothesis is seen as career damaging, regardless of the evidence. He may be right. Or Oumuamua may turn out to have a natural explanation we haven't identified yet, but something passed through our solar system that we cannot explain, and we named it Scout. Section 9. The cosmic perspective on observation. Let me step back from specific anomalies for a moment and address a deeper question. Even if civilizations exist, why would they bother watching us? This question only seems obvious until you actually think about what observation means at civilizational scales. Consider what we do. We send probes to Jupiter's moons looking for life. We photograph the surface of Mars in extraordinary detail. We are planning missions to collect material from Saturn's moon Enceladus, where we've detected organic molecules and a subsurface ocean. We build radio telescopes to listen for signals from distant civilizations. We're developing space telescopes specifically designed to analyze the atmospheres of planets around other stars, looking for chemical signs of biology. We do all of this while we are, by cosmic standards, completely primitive. We have existed as a technological species for less than 0.001% of the universe's history. We've had space travel for about 70 years. We've been doing radio astronomy for about 80 years. And in that tiny, infinitesimal sliver of time, we have already developed sophisticated observation technology capable of detecting chemistry on other planets light years away. We have already sent physical probes to 7 of the 8 planets in our solar system. We have already identified thousands of other planetary systems. Now scale this forward by 1,000,000 years. A civilization 1,000,000 years more advanced than us would have observational capabilities as far beyond ours as ours are beyond those of early hominids with stone tools. They would not merely be able to detect the chemistry of our atmosphere. They would be able to, in principle, map the surface of Earth in detail, monitor electromagnetic activity consistent with technological civilization, track the development of our technology over time, and analyze the biology of individual organisms. The question isn't, why would they bother watching us? The question is, why would they not? We are a fascinating datum, a young civilization at the threshold of technological development on a planet full of life at a critical historical juncture. Any civilization interested in the development of intelligence, which we can assume many would be since they were once where we are, would find Earth interesting. And the cost of watching is, for a sufficiently advanced civilization, essentially zero. You don't need to visit to observe. You just need instruments sensitive enough to detect what you're looking for. A civilization with a million-year technological lead might have monitoring capabilities spread across the galaxy, requiring no more of their attention than our satellite systems require of ours. There's something else worth considering. In ecology, we have the concept of indicator species, organisms whose health or behavior signals the state of the broader ecosystem. A canary in a coal mine is the classic example. The behavior of keystone predators tells you about the health of prey populations. The presence of certain insects tells you about the health of the soil. We might be an indicator species on a cosmic scale. The way Earth's biosphere develops, whether it achieves technological civilization, whether that civilization survives its technological adolescence, whether it joins the broader pattern of civilizations in the galaxy or destroys itself, might be intensely interesting information to those who have watched many civilizations go through similar stages. We are the experiment. The watchers, if they exist, are the scientists. Section 10. The silence as evidence. I want to spend time on something that seems like it should be settled but isn't. What does the silence actually tell us? For decades, null results from SETI, pointing telescopes at the sky and hearing nothing, have been interpreted as evidence against extraterrestrial civilizations. The reasoning goes, if they're out there, we'd hear them. We don't hear them. Therefore, they're probably not out there. This reasoning has a name in logic, modus tollens. If P, then Q, not Q. Therefore, not P. It's valid. The problem is that the first premise, if civilizations exist, we'd hear them, is much weaker than it appears. It assumes that civilizations broadcast in ways we'd detect. But think about our own trajectory. We started broadcasting radio signals at the turn of the 20th century. But the nature of those signals has been changing continuously. Early radio broadcasts were powerful and omnidirectional. Modern communications are increasingly digital, compressed, frequency spread, and directional. As communication technology advances, the leakage of electromagnetic radiation into space decreases. We are becoming electromagnetically quieter as we become more technologically sophisticated. In another few centuries, we might be essentially invisible to distant radio telescopes that were looking for the kind of signals we broadcast in the 1940s. Extrapolate this to a civilization a million years ahead of us. Their communications technology would be so far advanced beyond radio that our attempts to detect them by listening at 1420 megahertz would be as naive as trying to detect the internet by listening for smoke signals. The silence might mean they use communication methods we haven't invented yet. There's a second problem with interpreting the silence as absence. SETI has covered an extraordinary amount of sky, but extraordinary is relative. As of now, the most comprehensive SETI searches have examined perhaps a few thousand star systems in reasonable depth. The Milky Way contains somewhere between 100 billion and 400 billion stars. We have looked carefully at a fraction of a percent of the available targets. Imagine you're standing on the coast of California, facing the Pacific Ocean. You extend your arm, point one finger at the ocean, and close one eye. The patch of ocean you can see past your fingernail is approximately the fraction of the Milky Way that comprehensive SETI searches have deeply examined. And we haven't heard anything, but we've been looking at a fingernail. The silence from SETI is not evidence of absence. It is evidence of the difficulty of the search. These are very different things. But there is one version of the silence that carries genuine weight. Not the silence of radio telescopes, but the silence of the universe itself. The fact that the galaxy doesn't look modified, that stars aren't being managed, that the largest observable structures in the universe, galaxy clusters, cosmic filaments, appear to be following purely natural gravitational dynamics without any sign of engineering. If even one civilization anywhere in the history of the universe had developed to the point of engineering at cosmic scales, the scale where you redirect the output of stars, reshape the structure of galaxy clusters, harvest the energy of dark matter, we might expect to see it. Unless civilizations universally don't survive long enough to reach that stage, or unless they reach it and then stop, or move inward rather than outward, or evolve into something that doesn't leave the traces we'd expect, or unless they are watching from a level of concealment that our instruments simply cannot penetrate. Every interpretation of the silence leads back to the same uncomfortable place. We don't know. And not knowing, given everything else we know about the scale and age of the universe, should unsettle us. Section 11. What would watching look like from the inside? Here's a question I want you to sit with. If we were being watched, carefully, systematically, by one or more civilizations sophisticated enough to maintain concealment, what would our experience of that look like from our perspective? What would it feel like to be the observed species? Probably exactly like this. Consider a civilization capable of interstellar observation would have monitoring systems we cannot detect. They would know our location with precision. They would have records of Earth going back millions of years, longer, probably, than we can imagine. They would understand our biology, our social structures, our history, perhaps our individual psychology, at a level that would seem to us like omniscience. And they would watch. From our side, the experience would be: the universe appears natural, empty. We look out and see stars and galaxies and the cosmic microwave background and the lovely, terrible silence of space. We build better instruments and find more of the same. We search for signals and find nothing conclusive. We find one anomaly here, one inexplicable observation there, one interstellar object that doesn't quite make sense, one signal that remains unexplained, but nothing that rises to the level of proof. This is exactly what careful observation by a concealed civilization would produce. So, occasional hint, the persistent anomaly, the data point that falls just short. The watchers, if they exist, would not be careless. They would have had millions of years to learn how to observe without being detected. The art of surveillance on cosmic scales, leaving no trace, revealing no presence, maintaining perfect concealment, would be something they had perfected long before Earth had multicellular life. We would not be able to detect them, but we might detect the edges of their concealment, the places where the illusion isn't quite perfect, the data points that don't fit, the anomalies that accumulate just below the threshold of proof but never quite go away. Here's what I find genuinely strange when I look at the history of astronomy over the last 50 years. We keep finding things that don't quite fit. The WOW signal, Tabby's star, Oumuamua, the 1977 detection from Virgo by the Argentine team, the fast radio bursts that showed early structured patterns before being attributed to natural sources. The anomalous acceleration of Pioneer 10 and 11 that took years to explain. The various unexplained infrared excesses around certain stars. Each one has a natural explanation that most scientists accept. Each one, upon investigation, seems to resolve into something prosaic. But the resolution isn't always clean, and the anomalies keep coming. This might mean nothing more than the universe is complex, and complex systems generate occasional outliers. This is almost certainly the correct explanation for most of them. But it also means the evidence we would expect to see if we were being watched, persistent anomalies that fall just short of proof, looks very much like the evidence we actually see. That is not the same as saying we're being watched. But it's worth noting, and it's worth asking, if we were the watchers rather than the watched, if we had spent millions of years observing a young civilization on the verge of technological maturity, what would we do next? What comes after observation? That's a question for Part 2. Section 12. The rare Earth counterargument. Before we proceed to what observation might mean, we have to honestly address the strongest counterargument, the one that says, maybe no one is watching because there's genuinely no one there. Not hiding, not silent, not concealed, just absent. The rare Earth hypothesis, developed in detail by paleontologist Peter Ward and astronomer Joe Brownlee, argues that the conditions that produced complex life on Earth are not typical. They are extraordinarily, perhaps uniquely, rare. The argument isn't just that habitable planets are uncommon. It's that the full suite of conditions required for complex, intelligent life is so improbable that Earth may be essentially unique across a universe with hundreds of sextillion stars. Think through the list. Our Sun is a G-type star, relatively stable, with a long main sequence lifetime. About 80% of stars in the galaxy are red dwarfs, which are smaller, cooler, and more prone to violent flares that would strip the atmospheres from any close orbiting planets. We got lucky with our star type. We orbit at just the right distance for liquid water. The habitable zone is narrow, slightly closer, and we get a Venus, runaway greenhouse. Slightly farther, and we get a Mars, frozen and thin atmosphered. We sit in the middle. We have a large moon. The moon stabilizes Earth's axial tilt, preventing the kind of extreme wobble that would produce catastrophic climate swings. The moon is the result of a specific early collision, a Mars-sized body striking proto-Earth at just the right angle. This is a contingent event that didn't have to happen. We have Jupiter. Our solar system's gas giant acts as a gravitational shield, deflecting comets and asteroids that would otherwise bombard the inner solar system at lethal frequency. Without Jupiter, complex life on Earth might have been repeatedly sterilized before it could develop intelligence. We sit in the galactic habitable zone, not too close to the center, where radiation and stellar density would be hostile to stable planetary systems. Not too far from the center, where heavy element abundances are too low for rocky planet formation. We have plate tectonics. Earth's moving plates recycle carbon dioxide through the mantle, acting as a long-term thermostat that has kept temperatures stable enough for complex life across billions of years. Most rocky planets probably don't have tectonics. Multiply these probabilities together, each individually somewhat unlikely, and the product could be extraordinarily small, perhaps smaller than 1 in the number of planets in the observable universe. If rare Earth is correct, the Fermi paradox dissolves. There's no paradox. The universe is silent because the universe is empty, not of simple life, perhaps. Microbial life might be widespread, but of complex, technological, communicating civilization, there might be no watchers because there are no beings capable of watching. I want to be honest about this. The rare Earth hypothesis is taken seriously by many researchers. It is not a fringe idea, and it explains the Fermi paradox without requiring concealment or silence or dark forests or zoo agreements. But here is where I think the honest conclusion lands. We don't know which is right. We have a sample size of 1. We know of exactly 1 planet with life, 1 civilization, 1 example of intelligent observation. From a sample of 1, we cannot calculate the frequency of the phenomenon. The rare Earth hypothesis might be correct. The cosmic abundance hypothesis, that life is widespread, that intelligence emerges regularly, might be correct. We don't have the data to distinguish between them yet. What we do have is enough uncertainty that dismissing the possibility of cosmic observers on grounds that we're probably alone is not a scientifically defensible position. The probability might be low. But in a universe this large and this old, even low probability events happen. And the consequences of being wrong, of having observers who have been watching us for millions of years, would be among the most significant facts in human history. The question is worth taking seriously, and the evidence, ambiguous as it is, deserves careful examination. Because if something is watching us, we should probably want to know. And if nothing is watching, if we truly are alone in this vast, ancient, extraordinary cosmos, that might be the strangest and most sobering discovery of all. Section 13, the contact threshold. What triggers first contact? If civilizations are watching us, and we've established that this is at minimum a scientifically serious possibility, one of the most important questions is, what changes the calculation? What would cause a civilization that has been observing silently for millions of years to make itself known? This question has been thought about seriously, and the answers are more concrete than you might expect. In anthropology, there's a principle called first contact protocol. The idea that the moment of initial contact between 2 civilizations is among the most consequential events either can experience. We know this from Earth's own history. European contact with indigenous Americans, British contact with Andaman Islanders, every documented case of a technologically superior civilization encountering a less developed one. These contacts almost never went well for the less developed party. Not always because of malice, often because of disease, misunderstanding, resource competition, or the simple gravity of power differentials. The outcome was shaped as much by the timing of contact as by the intentions of the more powerful party. If there are civilizations sophisticated enough to have been watching Earth for millions of years, they would know this history. They would know from direct observation of many civilizations, presumably, that contact at the wrong moment can destroy what it intends to preserve. It can collapse the very thing that makes the observed civilization interesting. So the question becomes, what constitutes the right moment? Several researchers have proposed different thresholds. The most commonly discussed is the development of self-destructive technology without the corresponding wisdom to manage it. We are currently in that phase. We have nuclear weapons capable of ending civilization. We are rapidly developing artificial intelligence that we don't fully understand. We are altering the climate of our planet in ways we cannot fully predict or control. This is arguably the most dangerous period in the development of any technological civilization. The gap between technological capability and social wisdom, between what a civilization can do and what it should do, is at its widest precisely when civilizations are where we are now, young enough to be reckless, powerful enough to be dangerous. Some researchers have speculated that this threshold, surviving technological adolescence, is itself what determines whether a civilization is deemed ready for contact. If we get through it, the quarantine lifts. If we don't, the nature reserve has one fewer species. Another proposed threshold is the development of certain specific technologies. Interstellar travel capability, for instance. A civilization that can leave its own solar system has changed its relationship to the rest of the galaxy. It's no longer a local phenomenon. It has the potential to become part of whatever interstellar community exists. A civilization capable of traveling between stars cannot reasonably be kept in a zoo. It will eventually go out and find what's there. At that point, the question of contact becomes unavoidable. Better to make it controlled than to have it happen accidentally. There's a third threshold that I find the most interesting: the development of communication capable of receiving signals on the appropriate channels. If civilizations are monitoring Earth and are interested in making eventual contact, there would be certain conditions under which they might begin communicating. One of those conditions might be when Earth civilization develops the technology to receive communication at the modalities they use. Not radio. They've long since moved past radio. But perhaps quantum communication, perhaps optical channels, perhaps some modality we're just beginning to develop. The moment we develop the right receiver, the signal appears. This is a testable hypothesis in principle. If we build quantum communication networks and suddenly detect structured signals, we can't explain through classical sources, that would be informative. If we develop direct brain-computer interfaces and consciousness expansion technology, and our subjective experience of reality changes in ways consistent with increased information density, that would be informative. I'm not suggesting these things are happening. I'm noting that the hypothesis has the form of a scientific prediction. Specific developments in our technology would be followed by specific observable changes in what we can detect. And I'm noting that we are, right now, in the middle of the most rapid technological development in our history. We are building quantum computers. We are developing AI systems of unprecedented capability. We are launching space telescopes sensitive enough to detect industrial chemicals on planets in other star systems. If there's a contact threshold, we might be approaching it. Section 14. The simulation argument and its implications for watchers. There's one more framework for thinking about cosmic observation that deserves serious treatment, because it reframes the entire question in a way that is simultaneously more radical and more mathematically grounded than anything else we've discussed. What if the watchers are not in the universe with us? What if they are running the universe? The simulation hypothesis, originally formulated rigorously by philosopher Nick Bostrom in 2003, begins with a simple observation. If it is possible to simulate conscious minds computationally, then sufficiently advanced civilizations will eventually do so. And if they do, they will create many simulations. Many simulated minds, living in many simulated realities, will exist for every real mind living in base reality. The math follows. If simulations are possible, then the overwhelming majority of minds that exist will be simulated. The probability that any given mind, including yours, is in base reality rather than in a simulation is therefore very small. Bostrom's original argument was about civilizations simulating their own ancestors. But the generalization is broader. Any sufficiently advanced civilization might simulate universes as experiments, as art, as entertainment, as research. And in each of those simulated universes, conscious beings would exist who believe themselves to be real, who look up at their sky and wonder whether anyone is watching. They are, obviously. The simulators are watching every simulated universe they've created. Now, I want to be precise about what this means and doesn't mean. The simulation hypothesis, if true, doesn't mean our universe is fake in the sense of being illusory. The chemistry and physics of our universe follow consistent rules. The electrons in your neurons are real electrons, following real quantum mechanics, producing real consciousness. The fact that the underlying substrate might be computation rather than base reality matter doesn't change the phenomenology of experience. What it does change is the relationship between our universe and whatever is outside it. If we're in a simulation, then the boundary of our observable universe is not the boundary of existence. There is something beyond, not accessible to us from within our universe, but real in its own terms, that contains the minds running our simulation. Those minds are, in the most literal possible sense, watching us. And here's what makes the simulation hypothesis scientifically interesting rather than merely philosophical. It has testable implications. A simulated universe running on computational substrate should, at sufficiently fine scales, show discretization. If space-time is not truly continuous, but implemented on a computational grid, there should be a finest-grained scale below which the laws of physics break down or change character. We know that space-time does have an apparently fundamental scale. The Planck length, about 10 to the power of minus 35 meters, and the Planck time, about 10 to the power of minus 44 seconds. Below these scales, our current physics fails. This is usually explained as a sign that we need a better theory of quantum gravity. But it is also consistent with what you'd expect from a computational substrate with finite resolution. A simulated universe would also, presumably, conserve computational resources. Complex, unobserved regions of the simulation might be rendered at lower resolution than observed ones, just as modern video games render distant objects with less detail than nearby ones. This might produce subtle signatures, inconsistencies in the physical properties of regions that are never carefully observed, or slight violations of conservation laws that resolve when examined closely. Some physicists have argued that quantum mechanics itself, specifically the measurement problem and wave function collapse, looks like a resource conservation algorithm. Quantum systems exist in superposition, in an unresolved state requiring minimal computational representation until they interact with other systems. At the moment of interaction, the state resolves. This is exactly what you'd design if you were trying to simulate a universe efficiently. Again, this has conventional explanations. Most physicists would say, quantum mechanics is just quantum mechanics, not a simulation. And they're probably right. But probably leaves room. And the simulation hypothesis has the unusual property of explaining, in a single framework, both the question of who's watching and the question of why the universe has certain strange features. If we're in a simulation, we have been watched since the first moment of computation. Every photon, every elementary particle, every thought has been observable in principle by whoever is running the simulation. Not necessarily watched in detail, that would be computationally expensive, but observable, accessible, recorded. This is either the most comprehensive answer to is someone watching us, or the most unfalsifiable one, depending on your perspective. I bring it up not to advocate for it, but because it's taken seriously by serious researchers. The Oxford philosopher Nick Bostrom has the argument in a prestigious academic journal. Elon Musk has publicly stated he thinks we're probably in a simulation. Neil deGrasse Tyson gives it odds of better than 50%. Avi Loeb, who we discussed in the context of Oumuamua, has written about it thoughtfully. It belongs in any comprehensive treatment of whether something watches us, because if it's true, the answer is yes, definitively, comprehensively, inescapably. Section 15. SETI's evolution from radio to everything. For most of its history, SETI, the search for extraterrestrial intelligence, was synonymous with radio telescopes. Point a dish at a star, tuned to the hydrogen line frequency. Listen. This approach was elegant in its reasoning. Radio waves travel at light speed, penetrate interstellar gas, and hydrogen frequency is a universal cosmic landmark that any technological species would know. It also produced exactly one genuinely anomalous result in 60 years of searching, the wow signal, and nothing else. By the 1990s, some researchers were growing frustrated. Not with SETI's ambition, but with its narrowness. We had been looking for one type of signal from one type of transmitter at one range of frequencies. What if we were looking in the wrong place, the wrong way, with the wrong instruments? The shift to technosignatures, the broader framework we discussed in Section 6, was one response. But there have been others, more radical ones, that represent a genuine reconceptualization of what it means to search for intelligence in the cosmos. One of the most interesting, we might be looking too locally. Instead of searching nearby star systems for signals that resemble our own technology, we should be looking at the universe on larger scales for signs of what happens when civilizations persist for very long times. Astrophysicist Jason Wright at Penn State has led some of the most creative thinking here. He has argued that if technological civilizations persist for long enough, millions or billions of years, the most natural thing they might do is expand. Not just to other planets, but to other star systems. And expansion at civilizational scales would leave traces. Stars produce energy through fusion. That energy is mostly radiated into space and lost. A civilization interested in harvesting maximum energy from the universe would, if it could, modify this. Capture stellar energy before it escapes, redirect it, use it. On the scale of a galaxy, a civilization that had been doing this for millions of years might have visibly modified the statistical properties of stellar populations. Stars would show unusual infrared excesses. Stellar evolution patterns would deviate from what natural physics predicts. The distribution of stellar luminosities might show anomalies. Wright and colleagues have systematically looked for these signatures in large astronomical databases. So far, no confirmed findings. But there are interesting outliers in some datasets that have not been fully explained. A second approach. Look for anomalous stellar motions. Stars follow gravitational dynamics that we understand well enough to predict orbits with high precision. If some stars are moving in ways inconsistent with gravity alone, ways consistent with, say, a Shkadov thruster, a mirror that causes asymmetric radiation pressure and allows a civilization to slowly steer its stellar system, we should be able to detect this. The ESA's Gaia satellite has now mapped the positions and proper motions of over 1 billion stars with extraordinary precision. Researchers have combed through this data looking for statistical anomalies in stellar motions. Some have been found and attributed to natural causes. A handful remain unexplained. A third approach has been developed most recently by Beatrice Villaroel at the Stockholm University, who led a project searching for stars that appear in old photographic sky surveys and then simply disappear in modern observations. Natural stars don't disappear on human timescales. But a star that was harnessed, modified, or somehow used by a technological civilization might show unusual behavior, including, potentially, disappearance. The project has identified several candidate vanishing stars, objects visible in mid-20th century surveys that cannot be found in modern catalogs. Most will turn out to be measurement artifacts or misidentifications. But a few have survived initial scrutiny. None of these represent confirmed detections of alien technology. But taken together, they represent something important. We are now systematically looking for signs of intelligence at galactic scales, using instruments precise enough to distinguish natural from artificial at distances of thousands of light years. We are, for the first time, actually looking. Not just listening at one frequency, but looking at the sky as a whole, at the statistical properties of stellar populations, at the motions of billions of stars, at anomalies in the cosmic record. And the field is young. Gaia has been operating for about a decade. JWST has been operating for about 2 years. The Vera Rubin Observatory, which will image the entire southern sky every few nights with extraordinary sensitivity, is just coming online. The square-kilometer array radio telescope, when complete, will be more sensitive than all existing radio telescopes combined. We are in the early days of a genuine capability to detect cosmic intelligence. The null results so far don't mean much because we haven't had these tools for long. What happens in the next 20 to 50 years of systematic searching with instruments of this quality will be genuinely informative. If there's nothing to find, we should be finding nothing with increasing statistical confidence. If there's something to find, we should start seeing hints that resist explanation. The silence will become either more significant or less significant, and the difference will tell us something profound. Section 16. The ethics of observation. What do we owe each other? Here's a question that rarely comes up in discussions of cosmic observers, but matters enormously. What are the ethical obligations of those who watch? If civilizations have been observing Earth, watching our species develop, watching our history unfold, watching our wars and our art and our suffering and our genius, and they have chosen not to intervene, what does that mean about them? This question mirrors debates we have within our own civilization about the ethics of observation and intervention. When we observe a primitive tribe that has had no contact with the outside world, do we have an obligation to protect them, to share our medicine, to warn them of dangers? The dominant ethical framework in anthropology now says, minimize interference. The uncontacted peoples of the Amazon and other regions are, by international consensus, left alone. Not because we don't care about them, but because intervention without consent causes its own harms. The loss of culture, the introduction of disease, the disruption of ways of life that have their own integrity, these are real costs. But the framework isn't unanimous. When an uncontacted group is threatened by deforestation or violence, should we stand by and watch them be destroyed? The argument for non-interference meets its limit when the alternative is extinction. Scale this question to cosmic dimensions. If a civilization has been watching Earth for millions of years and has seen our history, has seen the Holocaust, has seen the slave trade, has seen plagues and famines and wars that killed millions, and has done nothing, what are we to make of them? One answer: they are correctly applying a principle of non-interference. They understand, from experience with many civilizations, that intervention causes more harm than it prevents. They are practicing a wisdom we haven't yet developed. Another answer: they are not moral agents in any way. We'd recognize. They are observers the way scientists observe, without experiencing the moral weight of what they see. They watch our suffering the way we watch the suffering of animals in nature, with interest, perhaps with something like compassion, but without a sense of obligation to act. A third answer: they are watching and waiting, not indifferent, not merely curious, but genuinely constrained by something, perhaps their own ethical frameworks, perhaps the terms of some cosmic agreement, from intervening until certain conditions are met. A fourth answer: they have intervened, subtly, in ways we don't recognize as intervention. They haven't stopped our wars or cured our diseases, but they've nudged at critical moments, given a scientific insight to the right person at the right time, prevented a catastrophic technology from being discovered before we were ready, shaped the history of our civilization in ways invisible to us but deliberate from their perspective. We have no way to distinguish between these possibilities from our vantage point. We can't see the watchers. We can't ask them their intentions. We can only observe our own history and wonder whether it unfolded as it did by chance or by something more deliberate. This ethical dimension matters because it changes what we hope for when we ask whether someone is watching. We don't just want to know if they exist. We want to know what kind of beings they are, whether their watchfulness is benevolent or exploitative, protective or predatory, interested or indifferent. And the answer to that question, if there is an answer, would tell us something not just about them, but about the moral structure of the universe itself. Whether the cosmos is the kind of place where old civilizations protect young ones. or whether it's a place where might makes right and observation is just the prelude to interference of the worst kind. I don't know the answer. No one does. But I think the question reveals something important. Asking, "Is someone watching us?" is not just a scientific question, it's a moral one, and the two cannot be separated. Section 17. What contact would actually mean? Let's indulge a thought experiment. Suppose we found definitive, unambiguous, confirmed evidence that we are being watched. Not a maybe, not an anomaly that might be natural, but proof. A message in a clear mathematical code or a structure in our solar system that could only be artificial, or a communication that leaves no room for doubt. What would actually happen? The immediate reaction, if history is any guide, would be chaos, but not the chaos of panic, the chaos of interpretation. A discovery this significant would be immediately contested. Multiple groups would claim the interpretation was wrong. Skeptics would argue the evidence was misread, contaminated, fabricated. Different religious traditions would interpret the discovery through their own frameworks. Governments would attempt to control the narrative. Social media would generate 1,000 conflicting theories within hours. The scientific community itself would be divided, not about whether the evidence was real, but about what it meant. Does contact mean benevolence, danger, indifference? Does it change our responsibility to act differently as a species? Within weeks, political consequences would follow. The discovery would be weaponized for domestic political purposes before any coherent international response could be organized. Some governments would see it as threatening, evidence of power they don't control. Others would see it as opportunity. Some leaders would claim it validated their worldview. Others would deny it entirely. The economic effects would be profound and unpredictable. Markets would react to uncertainty. Long-term investment decisions would be thrown into question. The entire framework of strategic planning, for nations, for corporations, for individuals, would need to be revised in light of the new information. In the longer term, months to years, something more interesting would happen. Humans are remarkably adaptable. We absorb extraordinary information and find ways to integrate it into our functioning. The discovery of confirmed extraterrestrial observation would eventually simply become part of the context in which we live. History provides an imperfect but suggestive parallel. When Copernicus proved that Earth orbits the Sun, rather than the reverse, the initial reaction was controversy and resistance. But within a few generations, humanity had entirely reorganized its self-understanding around the heliocentric model. The knowledge changed how we thought about ourselves, our relationship to the cosmos, our religious and philosophical frameworks. It did not end civilization, it deepened it. Confirmation that something is watching us would be a Copernican revolution of far greater magnitude. The realization that we are not merely observed by each other, that we exist within a context larger than our solar system, that our development has been witnessed by minds far beyond our comprehension. This would transform every field of human thought. Philosophy would have to grapple with the question of what it means to be human in a universe populated by beings so much older and more capable than us. Religion would have to reconcile its frameworks with the existence of intelligences that are effectively omniscient from our perspective. Science would have a new research program, understanding the nature of the observers, learning from their knowledge, eventually attempting communication. Ethics would be revolutionized. Every discussion of our responsibilities to future generations, to other species, to the environment, would now have to be conducted in the shadow of the question, what do the watchers think of us? Are we meeting some standard they apply? Are we failing it? And there would be the question of reciprocity. If they've been watching us, if they know our history, our biology, our social structures, our capabilities, and our failures, what would we want to know about them? What would be the first question humanity asks a civilization that has been watching us for 1,000,000 years? I think the first question, ultimately, would not be a scientific one. It wouldn't be, what is the nature of dark matter? Or, how do you achieve faster than light travel? It would be simpler and more fundamental. Did we make it? Through all the crises and catastrophes of technological development, did we survive? And in surviving, were we worthy of survival? Were we the kind of beings the universe could be proud of? And what would we do if the answer was no? Section 18, the anthropic shadow. Here's something that physics and cosmology have grappled with in the last few decades, and that has direct bearing on our question. It's called the anthropic principle, and it has a disturbing application to the question of cosmic observers. The anthropic principle begins with an observation. We can only observe a universe that permits our existence. If the fundamental constants of physics were even slightly different, if gravity were stronger, if the electromagnetic force were weaker, if the cosmological constant were larger, the universe would not contain stars or planets or atoms complex enough for chemistry, or chemistry complex enough for biology. We observe a universe fine-tuned for life because we couldn't exist to observe any other kind. This isn't a supernatural claim. It's an observational selection effect. Of all the possible universes, we necessarily inhabit one that permits us. Now apply this to the question of civilizations. We necessarily observe a universe in which we exist as observers. We exist at this particular moment in cosmic history. We are this particular kind of intelligence. But here's the disturbing application. Suppose there is some process, some class of events that regularly terminates civilizations. A great filter, in the language of Robin Hanson, who first formalized this idea. This filter is whatever kills civilizations before they become interstellar. If the filter is in our past, if we've already passed through the phase of development that destroys most civilizations, then we might be exceptional. We survived something that almost no one survives. This would explain the Fermi paradox. Most civilizations die young, we got lucky, and we now survey a galaxy mostly empty of other survivors. But if the filter is in our future, if the thing that destroys most civilizations is something we haven't yet encountered, then the fact that we exist right now, at this particular moment of apparent flourishing, tells us nothing reassuring. We're in the period of observation. We exist to observe. The filter is coming, and it will claim us as it has claimed all the others. Under this reading, the great silence is not evidence that we're alone. It's evidence of something worse, that the cosmos is littered with civilizations that made it this far, developed technology, looked out at the stars, began asking whether anyone was watching, and then didn't survive what came next. The anthropic shadow falls over every civilization, at the moment it starts asking these questions. You can only ask whether someone is watching if you've survived long enough to ask. But survival to this point doesn't mean survival through what's coming. This has a specific and disquieting implication for the watchers. If advanced civilizations exist and are watching us, they would know about the Great Filter. They would know the statistics. They would have watched civilizations reach this exact developmental stage, the stage of radio astronomy and nuclear weapons, and climate disruption and artificial intelligence, and they would know what fraction of civilizations make it through. They would be watching us the way you watch an animal at a critical moment, trying to cross a river full of predators, or survive a drought, or give birth to vulnerable young. Not with indifference, with something between hope and sorrow, because they would know, with a statistical certainty we can't yet access, whether we are likely to make it. And we don't know if they're rooting for us or simply recording the outcome. Section 19. What we should do about it. Let's get practical. Assume we take seriously the possibility, not the certainty, but the genuine possibility, that something is watching us. What should we do differently? This is not a question for science fiction. Several serious researchers have addressed it directly. The first and most important implication is behave as if we're being watched. Not in a paranoid sense, but in the sense that our actions as a civilization are being recorded and evaluated by observers we don't fully understand. We should want to be the kind of civilization that, if observed, appears to be worth preserving. This sounds abstract, but it has concrete meaning. A civilization that destroys its own environment, that develops weapons of mass destruction faster than it develops the wisdom to manage them, that fails to extend care to its own members. Such a civilization might not strike observing minds as one that should be granted contact or protection. We don't know if this matters, but we don't know that it doesn't. And the baseline case for treating each other well, for managing our environment responsibly, for developing technology with wisdom, these cases rest on their own merits. The possibility of observation simply adds another argument to an already strong case. The second implication is look more carefully and with better instruments. The SETI enterprise needs significant expansion, not because we're likely to find something immediately, but because the cost of not looking, of missing evidence that was always there, is extraordinarily high. We should be building the next generation of radio telescopes. We should be designing space telescopes specifically for technosignature searches. We should be systematically analyzing existing datasets, the terabytes of astronomical data already collected, with artificial intelligence capable of finding patterns that human researchers would miss. The Breakthrough Listen project, funded by Yuri Milner and directed by Avi Loeb among others, is doing some of this. It has devoted significant resources to the most comprehensive radio and optical SETI search in history, but it remains drastically underfunded relative to the importance of the question. Third, develop a contact protocol. If we detect something, a signal, an anomaly, a structure that can't be explained naturally, we need agreed-upon procedures for how to respond. Who verifies the detection? Who communicates on behalf of humanity? What do we say? What languages, what mathematics, what values do we represent? These are not rhetorical questions. They require actual answers developed through international deliberation before we're faced with the real situation. Making these decisions in the aftermath of a detection would be chaotic and probably produce outcomes no one intended. Fourth, develop a framework for thinking about the ethical implications of contact before contact occurs. What do we owe any beings we encounter? What are we prepared to offer? What are our limits? What would we refuse? And what would we accept? We have frameworks like this for ordinary diplomacy, for international law, for trade agreements. We need something analogous for the situation of encountering beings vastly more capable than us. Fifth, be honest about uncertainty. The single biggest obstacle to productive engagement with the question of cosmic observers is the dual failure of credulity and dismissal. On one side, people who accept alien visitation without evidence. On the other, people who dismiss the possibility without engaging with the genuine scientific arguments. The honest position is, we don't know. The universe is large enough and old enough that observers could exist. The evidence is genuinely ambiguous. The stakes are high enough that we should invest in finding out, and we should not let discomfort with the question prevent us from taking it seriously. Section 20. The technology that could change everything. Before we get to the deepest possibility, there's something happening right now in laboratories and observatories and computing centers around the world that could fundamentally change the terms of this question within our lifetimes. Not in centuries, in decades. The James Webb Space Telescope is the most obvious example, and we've touched on it. But the scale of what it represents deserves full appreciation. JWST can analyze the chemical composition of an exoplanet's atmosphere from a distance of dozens of light years. It can detect molecular signatures in quantities of parts per billion, and it's operating right now, collecting data every day. In the coming years, JWST will systematically survey dozens of planets in the habitable zones of nearby stars. It will look for oxygen, methane, water vapor, carbon dioxide, biosignatures. But it will also look for things that shouldn't be there naturally. Industrial pollutants, synthetic gases, chemical combinations that only technology produces. We will know, with genuine scientific confidence within the next decade or two, whether the atmospheres of nearby exoplanets look biological or industrial. That is not a prediction about what we'll find. We may find nothing. But the capability to ask the question rigorously is new. It didn't exist 5 years ago. The Square Kilometre Array, the SKA, is under construction in South Africa and Australia. When complete, it will be the largest and most sensitive radio telescope ever built, composed of thousands of individual antennas spread over vast distances and combined through interferometry into a single instrument of extraordinary power. Its sensitivity will exceed all existing radio telescopes combined. The SKA will be able to detect radio leakage from a civilization at Earth's current technological level from a distance of several hundred light years. Not deliberate high-powered transmissions, just the ambient electromagnetic noise of an industrial civilization, the accidental broadcasting that we ourselves produce. If there's a civilization within a few hundred light years of us that uses radio technology even at our current level, we should be able to detect them. Several hundred light years sounds limited, but it encompasses thousands of stellar systems, and it represents a qualitative shift. For the first time, we'll be searching not for powerful, deliberate beacons, but for the kind of low-level electromagnetic signature that any technological civilization produces without trying. If the answer is silence even at that sensitivity, over thousands of star systems within a radius of several hundred light-years, that silence will itself be profoundly informative. And then there is artificial intelligence. The datasets we've accumulated in astronomy are extraordinary in scale. Decades of imaging surveys, spectroscopic surveys, radio data, infrared data, terabytes of information about billions of objects in the sky. Humans can only analyze a fraction of this directly. Most of it sits in archives, examined only by automated pipelines designed to look for specific things. AI systems capable of unsupervised pattern recognition, the kind that doesn't require knowing what it's looking for in advance, can examine this data for anomalies that don't fit any known natural model. They can find things that human researchers, constrained by their existing categories and expectations, would miss. Several projects have already begun this work. They are finding anomalies. Mostly, these anomalies get explained by better understanding of natural phenomena. But the process of looking systematically, without preconceptions, at enormous datasets is the right process. And as AI capabilities improve, the thoroughness and sensitivity of these searches will increase dramatically. We are, right now, in the early days of a genuine capability to search for intelligence in the cosmos. The tools that exist today are the best that have ever existed and the worst that will ever exist. Every year, they get better. Every year, the sky becomes more transparent to our instruments and our algorithms. Within 50 years, the span of a scientific career, the lifetime of someone reading this today, we may have looked at enough of the sky with enough sensitivity, across enough modalities, to make a statement about the prevalence of technological civilizations that carries genuine statistical weight. We may find nothing. That will be important. We may find something. That will change everything. Either way, the age of informed ignorance about this question is ending. The age of data is beginning. And data, whatever it shows, is better than silence. Section 21. The deepest possibility. Let me end the sections with something that I think is the deepest and most beautiful version of the question we've been asking. What if the universe watches itself? This isn't mysticism. It comes from a serious strand of physics developed by John Archibald Wheeler, one of the giants of 20th century theoretical physics. Wheeler spent much of his later career thinking about what he called the observer participancy of the universe. The idea that observation is not merely passive reception of a pre-existing reality, but an active constitutive element of reality itself. In quantum mechanics, the measurement problem has never been satisfactorily resolved. Why does the act of observation cause quantum systems to adopt definite states? What counts as an observer? Does observation require consciousness or just interaction? These questions have been debated for a century without consensus. Wheeler took seriously the possibility that consciousness and observation are genuinely fundamental to the structure of reality, not epiphenomena, not late additions to a universe that was already complete, but ingredients in the very process by which the universe exists in the way that it does. His framework was called the participatory anthropic principle, and it went further than the standard anthropic principle we discussed earlier. Not just, we necessarily observe a universe compatible with our existence, but conscious observers are necessary for the universe to have the kind of definite existence it appears to have. Under this view, the universe brings conscious observers into being because it needs them. Not in a teleological, intentional sense. The universe doesn't have goals, but in the sense that the structure of physics selects for conditions that produce observation, because a universe without observation is, in some fundamental quantum mechanical sense, indeterminate, unresolved, not yet real in the full sense. If this is even partially right, and I emphasize that it remains controversial, it transforms the question, is someone watching us entirely? It's not that someone in the universe is watching us from outside. It's that the universe is watching itself through us. Through every conscious mind, in every corner of the cosmos. Every act of observation, every moment of awareness, every mind that has ever looked at the stars and wondered, all of this is the universe in the act of making itself real. We are not the observed. We are not merely the observers. We are the mechanism by which a vast quantum system resolves itself into a world of definite, experienced, meaningful fact. And if this is true, then whether or not there are alien civilizations watching Earth through their instruments, and there may well be, there is something more fundamental than that happening. The cosmos is watching itself, has always been watching itself, cannot do anything other than watch itself, because the watching is how it exists. This might sound like physics has wandered into mysticism, but the equations that motivate it are real quantum mechanics. The questions are genuine philosophy of physics, and the implications are that consciousness and observation may be more tightly woven into the fabric of reality than our ordinary materialist framework allows. It gives a different answer to our original question. Not yes, alien astronomers are watching from distant worlds, though they may be, but something older and stranger. The universe is aware, in some structural sense, of its own existence, and every mind that has ever turned upward and wondered is participating in that awareness. You are not just the observed. You are part of how the universe sees itself. Conclusion. So, is someone watching us? The honest answer is, we don't know, and that we don't know is more loaded, more significant, and more scientifically interesting than it might seem. We know the universe is 13.8 billion years old. We know it contains hundreds of sextillions of stars. We know most of those stars have planets. We know the chemistry of life is widespread in the cosmos. We find the building blocks of biology in interstellar clouds and on meteorites. We know life on Earth arose almost as soon as conditions permitted. We know our galaxy is old enough that a civilization just slightly ahead of us in development, by 1 million years, would be as incomprehensible to us as we are to bacteria. We know such civilizations, if they exist, would have had more than enough time to detect Earth, to map it, to monitor it, to understand everything about us. We know the Fermi paradox is real and unresolved. We know the Great Silence is a genuine puzzle. We know the wow. Signal remains unexplained. We know Oumuamua had properties inconsistent with all known natural objects. We know Tabby's star produced anomalies that still aren't perfectly understood. We know our technosignature searches have barely begun. We don't know whether observers exist. We don't know whether the silence is evidence of absence or concealment. We don't know whether Oumuamua was technology or something natural we haven't yet characterized. We don't know whether the wow signal was a genuine transmission or a one-time natural phenomenon we haven't since encountered. But here's what I think is most important. The question matters. Not just as a curiosity, not just as a driver for science funding, but as a genuinely transformative question for how we understand our place in the cosmos and how we make decisions about our future. If we are alone, if no one is watching, if we are the only minds in this vast observable universe, that is the most awe-inspiring and terrifying fact imaginable. It would mean that all of consciousness, all of experience, all of the universe's capacity for self-awareness rests here, on this pale blue dot. The responsibility that comes with that would be almost incomprehensible. We could not afford to fail. We would be the only experiment that had ever succeeded. If we are not alone, if something out there has been watching, waiting, perhaps wondering what we'll do, that changes everything else. Our development takes on an additional dimension of meaning. Our choices echo beyond ourselves. We are part of something larger, something we don't yet understand, something that may be more beautiful or more dangerous or more strange than anything we've yet imagined. Either way, the answer demands our full attention and our best science. Either way, looking up at the night sky and asking whether anything looks back is not a foolish act. It is one of the most important things a mind can do. Because the day we get an answer, and I believe we will get an answer in our lifetimes or our children's, will be the most significant day in the history of our species. And what we do with that answer will define what we become. Keep watching the sky. Something, somewhere, might be watching back. And when we finally see each other clearly, when the long, strange silence breaks, the universe will never be the same. If you made it this far, thank you for watching. Drop a comment with what you think. Are we alone, or is something out there? And what would you want to ask the watchers if you could? I'll see you in the next one.